All right, lesson 38, reciprocal, quotient, and Pythagorean identities. All right, so what are we doing here? So in trigonometry, there's things called identities that are just going to make it so that we can simplify things, right? And what an identity really is just, well, here, I'll show you down the bottom here. This is on your formula sheet. Well, skipping way down. You guys will have like this whole section. All of this is on your formula sheet, right? And we haven't really used many of them up until now. Like we've kind of used some of these. We use the angle identity there, or angle formula, I should say. We've used some of these, but we haven't really got into like any of this stuff. So now that's really what we're talking about now. We're going to be using all these different identities. And what that is that we can start, like if we ever get like a case like this, where we've got like 1 plus tan squared theta, we can, if we like, we can rewrite that as sine squared theta, because that might make things easier, right? So this section, well, I often say it's like a puzzle, right? Like these questions, we get, you know, some sort of question, and then we get, these are the pieces of my puzzle, so I can like use them to throw like into here and there and try to make something else out of it. But yes, it is a lot of trial and error and that kind of stuff going on too. So some kids find this unit a little uncomfortable because it's not going to be the case that, like, you know, you get something like, let's say, this question when we get there, where there'll be just one way to do it. So you can't just memorize the one way to do it. You have to actually be able to, like I said, like piece the puzzle together to solve for it. But we'll get there. So yeah, so here's some suggestions of how to proceed when we're doing these identity questions. So number 1 says replace trigonometric ratios with equivalent expressions that contain sine and cos, right? So we kind of want to break it down into like the simplest form we can. I don't like thinking in terms of like cosecant, secant, or even tan and cotan. I don't like, it's hard for me to picture what's going on there. So I like to break it down sine and cos whenever I can. Look for Pythagorean identities that can be replaced. So that's just one of those specific identities that I'll get to in a minute. And then we might need to manipulate them, creating like common denominators, you know, like we'll just do some algebraic manipulation to get there. Be inventive, right? There's, like I said, there's more than one way to do this. Yeah. And then when asked to prove or show that one side is equal to the other, then what we have to do, or what we should do, is work with the more complex side and try to get it to match to the less complex side. And again, none of that, some of that might not have made much sense, but I'll show you when we get a little bit lower what we mean. All right, so reciprocal identities. We've actually covered some of these, right? These are on your formula sheet, but you'll probably start memorizing these pretty quick, right? So I won't go into those. Actually, in the quotient identities, same thing. We've done these. Tan is equal to sine over cos, and cotan is flipped upside down, right? Cos over sine. All right. So doing some examples here. So let's do this first one. So it says, given this equation, cosecant theta is equal to cotan theta over cos theta. It says determine any non-permissible values of theta. It doesn't even actually want us to just solve this one yet. It just wants us to say what angles of theta are not allowed. So really in this unit, there's only really for us 2 situations where we have to think about non-permissible values. And that's, you can't take the square root of a negative, which we're not really doing that at all here, right? And the other one is you can't divide by 0. So that's really what we're saying is, like, when would I be dividing by 0 in any of these cases, right? So again, what I want to do is I want to change this cotan and I want to change this cosecant theta into terms of sine and cos, so that because I can figure out using my unit circle, you know, where those things are equal to 0. So that's the idea. So let's rewrite this instead of a cosecant theta. So cosecant is the same thing as 1 over sine theta. So I'm going to write that out as 1 over sine theta. That's right on your formula sheet. So I just replace that with this, okay? Okay, and then the next part, cotan theta. So cotan theta is the opposite of tan. So this one is going to be cos theta over sine theta. Okay, and then what I do quite often is, just so I don't get confused here, because I'm gonna have like fractions over fractions. Since that was cotan theta and now that's this, I put that in brackets just to remind myself that, okay, that was, I replaced it with that, right? And then it's all of that over and then cos theta. Okay, so that looks a little bit confusing, but now all I'm doing for this part of it says, what are the non-permissible values of theta? So I'm really asking myself, so I look down here, sine theta is not allowed to be equal to 0, right? Because then I'd be dividing by 0. And so where does that happen? So sine theta is not allowed to equal 0. Where is sine theta equal to 0? So you should have, you'll start memorizing this a bit too, but if you need to, get the unit circle for now. Sine theta, remember, these are all of our like sine values. There are y values, right? So where are our y values equal to 0? Well, that's going to be right here, right? That's going to be at an angle of 0, right? We have no y value there. We've got no sine value there, right? And then it also happens at an angle of pi. Okay, so that's where, so according to this, we can't, theta is not allowed to be an angle of 0, and it's not allowed to be an angle of pi. But then if I carry that on, it's also not allowed to be 2 pi, you know, or 3 pi or 4 pi, right? So there's a pattern that's starting to pop up here. So what you'd say is that for this part of it, you'd say the angle is not allowed to equal, and then I'll write it this way, pi n, where n is a member of the integers. So then let's just figure out what that means. Just like think about that for a second. Pi times n, so n in this case could be 1, 2, 3, 4, right? So that would be, you know, 1 times pi would be pi. 2 times pi would be 2 pi. 3 times pi, right? But it also includes negative numbers. So if and 0 as well. So if I put 0 into that, then that would be an angle of 0, and it's not allowed to be that either, right? But it's also negative numbers, right? So it also would be true that I can't go the other way around. I can't start here and go to negative pi, right? So if this was like -1 that I threw in there, then theta is not allowed to equal negative pi. Or if I threw in -2, it's not allowed to equal -2 pi, which would be that way. Okay, so there we go. So that's the sine part of it. Okay, so that's true. It's not allowed to be that. And then it's also, well, I also have to look right here and say, well, it appears that we're not allowed to divide by when cos is equal to 0 either, right? Because I'm dividing by cosine theta. So cosine theta also can't be equal to 0. Okay, so where is cosine theta equal to 0? Okay, well, cosine theta is equal to 0. Well, remember, cos is like our x's, right? That's like my cos values. So it's equal to 0 there, and it's also equal to 0 there. So it's at pi over 2 and 3 pi over 2. So the way I'm going to write this one, so I'll say theta is not allowed to equal. And then there's more than one way to write this, but the way I'm going to write this is I'm going to write it like this, pi over 2 and then n, where n is a member of the integers. Because what that would account for would be if I'm starting at like pi over 2, right? This is like where I'm starting from. And then if I multiply that by 1, right, that would give me pi over 2. But if I multiply that by 2, right, if I put a 2 in for n, then that would bring me down here, right, which is also true. If I multiply that by 3, then that would take me right back up to here again, which is true, right? And it also works in the reverse. So if I multiply by negative, right? So negative would take me around the backside there. Yeah. One thing I'm noticing here, though, yeah, is that, yeah, we're actually not going to be able to do that, because what if we threw 0 in for that? Huh, I just found a mistake on mine. If we threw 0 in for that, then that'd say it can't be equal to 0. But so, oh yeah, I guess that, well, cosine can be equal to, or theta itself can be equal to 0, right? Because the angle itself would be fine to be at 0, right? So yeah, so that's not going to work. So actually, sorry, I should write this a little bit different. Let's write it like this. It'll be pi over 2 plus n times pi, where n is a member of the integers, right? So that'd be a little bit better. So now if n was 0, I'm still starting at pi over 2. So let's look at this one a little closer though too, right? This would be the same thing, right? But it just wouldn't include the number 0 as well. So hopefully that makes sense. Okay. Moving on. So now it says verify the equation for theta is equal to pi over 3. So what this means is that we've got this equation up here, all right? And it's saying that this side is equal to this side. Well, then that should be the case if I throw in pi over 3 in for theta everywhere in there, that the left side should be equal to the right side. So let's just try it out. So we'll say, and what I'm going to do is I'm actually going to throw in theta into this, actually, the way I've done this one down here. Now you don't really want, like I could here, right? I could cancel my cos theta and my cos theta, which is what I'm going to do in a second here, but I don't really want to do that because if it turns out like I always have to, like, if I'm going to put my number in for like whether or not it'll work, I have to do it before I actually cancel things out. Okay. So anyway, let's throw some numbers in. So I'm going to say 1 over, and now this would be sine of pi over 3. Okay, and that's supposed to be equal to cos pi over 3 over sine pi over 3 over cos pi over 3. Okay, now that looks super confusing, but here, put brackets around that again to kind of get your bearings there. So now let's figure out what those are. So sine pi over 3. So let's remind ourselves using the unit circle. So sine at pi over 3. So if I come over here and I look at pi over 3, right? That's this angle right here. So this is as easy as just choosing the sine value, right? Sine is the y value. So that's what that is, right? So sine of pi over 3 is root 3 over 2. So this is really 1 over root 3 over 2. Okay, maybe put that in brackets too to help you out there. Okay, and that's supposed to be equal to, and then cos at pi over 3. So cos at pi over 3 is a half. So we'll do that again, and I'll put in brackets again. So a half over, and then sine pi over 3 was root 3 over 2. And then over a half. Okay, ooh, that was weird. So now it looks confusing, but look here, I've got 1/2 on the top and I got 1/2 on the bottom. If you can see it, you can actually just cancel those right away, right? You can just cancel it like that. If you have a hard time kind of seeing that, that's okay. Remember that dividing by, this is a fraction down here, dividing by a fraction is the same as multiplying by the reciprocal. Okay, so what you could also do, I'm getting messy here, is you'd have, so 1 over root 3 over 2. And then you could rewrite this as is equal to 1/2, and then multiplied by the reciprocal there, right? So okay, so 1/2 multiplied by, and then so this will be my bottom, that will be, so 1/2 times 1/2 over root 3 over 2. I'm finding another mistake on here. Anyway, turns out that these ones aren't the same in this case, are they? Oh yeah, it is. What am I doing? Sorry, guys. So in this case, this would be, yeah, this just gets like really kind of complicated because it's like, yeah, anyway, what we should have done is just cancel these. These got a little bit convoluted because it was like cos pi over 3 over 1. So you'd flip that and then they'd cancel, right? So either way, you end up getting like the 1/2 canceling on the bottom. So you do end up with root 3 over 2. Sorry, I made that confusing. So even though, so that's looking good now, you could flip this up to the top too, and that's 2 over root 3 is equal to 2 over root 3. Okay, so it is an identity in that case. Typically, yeah, you wouldn't even really need to at that point, because we can also prove it using some of our identities and actually canceling things. So we can prove these things like 3 ways. You can put the number in and actually check, right? You can do it graphically, so you can actually graph it to see if it's gonna if it's true, and then you can also prove it just by like canceling things out and seeing if it's actually true in that case too. So the graphing way, I'm not going to do that, especially for the sake of time here, but the way you would graph that is kind of the way that we graph, that we've done it in the past, where you would do this. We could, in your calculator, you could graph this side as y1 and you graph this side as y2. Okay, so then if you did that, what you should see is that there's actually no difference between them. You'd see them like overlapping on top of each other. Now, a little bit of warning here when you do these though, is that this method won't actually tell you if they're exactly the same identities all the time. It's not actually like a really like legitimate proof, because let's say that I had like, you know, one graph that did, this isn't the graph, but let's say that it did something like this, right? And then you graphed another one and it was like exactly the same. It was on top of it. Well, that's actually not proof that they're exactly the same. And the reason for it is because remember that sometimes in our graphs, we have things called holes, right? There's actually, even though like it looks like it's a continuous graph all the way along, there might be a hole. There might be like a non-permissible value on one of the graphs, but not the other. So it's actually not completely accurate to just graph it and call it good. Okay. So like the best way to do it is actually to put the numbers in to actually see if they are equal. The left side is equal to the right side. Okay. So anyway, prove the equation is an identity for all permissible values of theta. Okay. So what we can do here is just starting from this point, right? When we were up here, we've got 1 over sine theta is equal to cosine theta over sine theta over cosine theta, right? And that was like a thing, right? Now, what we can do here, like I was saying above, if this is cosine theta over 1 on the bottom, then we can flip this guy around, right? Dividing by a fraction is the same as multiplying by the reciprocal. So I can rewrite this as 1 over sine theta, right? Just this side is equal to, and then flipping this around is cosine theta over sine theta, just the top here. And then instead of dividing, I'm going to multiply it by 1 over cosine theta. So now you can see that the cos thetas cancel. So I've got 1 sine theta is equal to 1 over sine theta. So there you go. Your left-hand side is equal to your right-hand side. So then we can say that the identities are the same. Okay. You would also state here what the non-permissible values were if you were doing this question, but I did that above already. So, all right, so moving on. So just lots of practice on these. So this one says, simplify the expression tan theta over cos theta over, or sorry, tan theta times cos theta over secant theta times cotan theta. All right, so looking at this, the general strategy that you want to use here is change these guys into terms of sine and cos if you can, right? So I'm going to change tan, secant, and cotan all to sines and coses. Okay, so instead of a tan theta, I'm going to write that as sine theta over cos theta, right? That is what tan theta is, right? And then it's that times cosine theta, and then all over, and now I'm looking at the bottom now. So secant theta, that's the same thing as 1 over cos theta. And then times, and maybe I'll put that in brackets, times cotan theta. Cotan theta is the reciprocal of tan theta, so it's actually cos theta over sine theta. All right, so looking at this, there's a bunch of things that we can just go to town canceling now. If I just look at the top by itself for a second, I can see I've got cos theta over cos theta. So that disappears, that makes it nice. And looking on the bottom here, I've got cos theta over cos theta. So let's simplify this up a bit. You've got sine theta, and if you like, you could say over 1 for a second, right? Just looking at the top there, over, and then on the bottom, we've got 1 over sine theta. All right. Dividing by a fraction, the same as multiplying by the reciprocal. So that's the same thing. I should be writing down too, right? Instead of across. I'm just doing that for room here. But yeah, I'm going to write it over here again. So now we've got sine theta over 1. And then flipping this guy upside down, that's the same thing as sine theta over 1. All right, well, that's really sine squared theta. Now, we haven't talked much about this, the way we write this too. Maybe this is the first time you've seen it. When I write sine squared theta, that's just a fancy way of writing sine functions, where it'd be the same thing as writing like this, sine theta squared. They mean the same thing. We just kind of write a little bit different when we're doing it. So either way. Okay, so that's it. So there's your simplified expression there. All right, new ones. So we got Pythagorean identities. So first off, it says prove these identities. These identities are on your formula sheet. That's these identities right there. So you guys will see these on your formula sheet there. Okay, this one's pretty straightforward actually for the first one. And what this comes from is if you had r squared is equal to x squared plus y squared. So just Pythagorean identity. And if you remember, like looking at your unit circle here, if I was looking at this, right, my hypotenuse has a length of 1, right? That's like my r value. So that's 1. And then up and down, that's my sine value. So sine theta. And across the bottom, that's my cos theta. So all the first equation is really saying sine squared plus cos squared is equal to 1 squared. So that's just Pythagorean identity. That's all this first one really is. So we can say, well, that's the same thing as saying 1 squared, right? The length on the unit circle is equal to cos squared theta plus sine squared theta. And there you go. We proved it. Okay, so let's prove the next one. So if we start off with our first identity, these two are just actually variations of the first. So if I started off like this and said, all right, we've got cos squared theta plus sine squared theta is equal to 1, then if I just pull this move, if I just say, well, why don't we try to divide everything by cos squared theta? So divide each term. So that one, so cos squared theta, and divide this by cos squared theta. Okay, so if I just simplify this up now, we've got cos squared theta over cos squared theta. They cancel, but really you've still got 1. So that's 1 plus, and now looking at this, sine squared theta over cos squared theta. Well, sine over cos is tan. So if it's sine squared over cos squared, that's actually just tan squared theta. And then 1 over cos theta is secant theta. So 1 over cos squared is secant squared theta. And there you go. There's our next identity. Here, move this. And then just for the next one, it's very similar. So we're going to say, if we start off with cos squared theta plus sine squared theta is equal to 1. And instead of dividing everything by cos squared theta, if we divide everything by sine squared theta, so divide by that, divide by sine squared theta, divide by sine squared theta, then we end up with, well, this, so cos squared theta over sine squared theta, that's cotan squared theta plus, and then that's just 1, is equal to, and then 1 over sine squared theta, that is the same thing as cosecant squared theta. There, we proved it. All three. They all come really just from the fact that you're making a right angle triangle, right? They all come from this idea, a squared plus b squared is equal to c squared. All right, so now using those, we can use those now to simplify things like this, right? So looking at this first one, I've got 1 minus cos squared theta, and then over secant squared theta minus 1. So this is where it can get a little bit tricky, right? Because what you might do, and it might actually work. You could do it this way too, but I think it'd be tougher, is you might say, well, secant squared theta, well, Mr. Brown was telling me I'm supposed to change that into terms of sine and cos if I can. And that would work. You could do that. It's going to probably get a little bit more confusing. So this needs to be something that you recognize. You're like, I've seen that before. Secant squared theta, something to do with 1. And then you come over here and be like, okay, secant squared theta, there's a 1 and a secant. This one's adding though, but what if I just rearrange that for a second? Let's just bring this 1 over to the right. Let's write this instead as tan squared theta is equal to secant squared theta minus 1. And then you're like, okay, looks good. Secant squared theta is equal to tan squared theta. So I could really replace this whole bottom with tan squared theta, right? So you're like, okay, so I'm on the right track there. And then same with this one. What about this? 1 minus cos squared theta. So 1 minus cos squared theta. So I'd be thinking, okay, cos squared theta, 1. This has, this is adding, and the one I'm looking for over here is subtracting. But like, so let's try to rearrange this a little. So what if I just rewrote this one as sine squared theta is equal to 1 minus cos squared theta, which is exactly what I was looking for, right? 1 minus cos squared theta. So that means an identity of 1 minus cos squared theta is sine squared theta. So I get to replace it with that, right? So I get to actually just rewrite this top bit as sine squared theta, okay? Over. Now the bottom, I already said that one. The bottom, secant squared theta minus 1. That's the same thing as tan squared theta. So the bottom here is tan squared theta. Now that is simpler, but I've got this written in terms of tan, right? I'm going to change that into terms of sine and cos to see if I can cancel something again. So let's write this. This is the same as sine squared theta over, and then tan is sine over cos. So tan squared is sine squared theta over cos squared theta. All right. Dividing by a fraction, same as multiplying by the reciprocal. So we can rewrite this as, in my room, sine squared theta times, and then flip this upside down, right? Now you've got cos squared theta over sine squared theta. So they cancel. So all of this was just equal to cos squared theta, right? So way simpler. Okay, next one. Sine squared theta plus sine squared theta times cotan theta. So, okay, let's write it out again here. So I've got sine squared theta. Can't really do much with that. I could, actually, you could do whatever you like. There's lots of options here, but I'm gonna leave it like that for a second. I'll say that plus. Now, let's just rewrite this one in terms, like this cotan, in terms of sine and cos for a second. Let's see if anything happens. See if we can do anything with this. So we've got sine squared theta, and then cotan is cos squared theta over sine squared theta. Okay, so in that case, we've just got, well, those cancel, right? So those get to cancel. So we've got sine squared theta plus cos squared theta. And that is more simple. And this is where some students would stop and say, okay, well, that's it. That's the simplified version. But you want to look over here again and see, is there anything? Can I rewrite that as anything? Right? And turns out you can, right? Sine squared theta plus cos squared theta, that's the same thing as 1. So I get to just call this all just 1. It's the same thing. All right, 2 more. Sine to the power of 4 theta minus cos to the power of 4 theta. All right, so now, sometimes they can look a little bit confusing, especially when it's like written in this new form that we're not really used to here. But just for a second, imagine instead of sines and coses that this was just x to the power of 4 minus y to the power of 4. All right, so maybe it's still not jumping out at you, but the other thing that what we can do here, this is actually, this is a difference of squares, right? to the power of 4 is a perfect square, and I'm subtracting. So if I was just to use, some of my factoring skills that you guys know, I could rewrite this as x squared minus y squared, and then x squared plus y squared, right? Just two different signs, negative, minus, and adding, right? Okay, so that would be the same thing. Let's, instead of x's and y's though, remember we were dealing with sines and coses. So let's write this out, but with sines and coses instead, right? I just did this just so it looked more familiar. But this would be the same thing as sine squared theta, right? Minus cos squared theta times, and then sine squared theta plus cos squared theta. And then looky here, sine squared theta plus cos squared theta, that's 1, right? That whole thing just gets canceled, really, essentially, because it's 1. So times 1 just doesn't, it's just kind of gone, right? So in the end, there's my answer, just right there. Now you might know this actually, that depending on what they want, like that is true. We could actually factor this again though too, can't we? This is a perfect square and that's a perfect square. So you could also write it again as sine theta minus cos theta times sine theta plus cos theta. You could do that, but tell you the truth, it doesn't actually do anything for us, right? We can't really do anything with those to simplify with the identities. So yeah, I think typically you'd probably leave it like that would be the most simplified, but that's kind of the problem too, is that some kids aren't really a big fan of this, where it's like, what's the right answer? Well, there is no like the right answer. There's like multiple versions of it, right? Like this is true, and so is that. They're one's simplified a little bit different than the other. So, okay, last one. Last one. All right, just looking at this. What can we do with this guy? So if I'm looking at this, I might be tempted to start thinking, okay, I could turn that into like tan theta. I could turn that into cotan theta. But is tan theta plus cotan theta equal to anything, right? And maybe you'll look at your formula sheet and you'll say, well, not really, right? I don't really have like tan theta and plus cotan theta giving me anything. So that actually wouldn't do us any good. So that's not the case. So typically the way that we're going to handle these ones, when you've got some fraction plus some fraction like this, and then it's over top of anything on the bottom, really, like it could be a fraction or whatever. What we want to do is we actually want to combine those two fractions under the same denominator, right? I actually want to make this a fraction with the same denominator. So here's what we're gonna do. I'm gonna write this again just so I can have it a little bit bigger too. So this is sine theta over cos theta plus cos theta over sine theta over 1 over sine theta. All right, so like I said, this is one of our tricks, one to see if things will work here, is I want to see if I can get this top guy all over the same denominator. So how do I get over the same denominator? What I have to do is I have to, well, find my common denominator. So the common denominator between this side and this side, right, is going to be cos theta times sine theta. And maybe it's worth kind of going over that. It'd be like I said this, if I had like 2 over 3 plus 4 over 2, and we wanted to figure out a common denominator for those guys, then what you could do is you could say, well, I'm going to multiply this side by 3, and I'm going to top and bottom, and I'm going to multiply this side by 2, top and bottom. We're going to use that same kind of logic here, where if I want to find a common denominator for this one and this one, well, I'm going to multiply this side by sine theta and the top by sine theta, right? Because I got to get that. That's the same as like multiplying this by 2 and 2, right? And then I'm going to multiply the other side here by cos theta, and then on the top by cos theta. All right, let's see what happens there when we do this. Okay, so moving on down, this bottom part, I'm just leaving that for a second, right? I'm just not even bringing that into it. So looking at the top here, let's just simplify the top part of it all out. So Now I've got sine theta times sine theta. That's the same thing as sine squared theta plus, and then cos theta times cos theta. That's the same thing as cos squared theta. I'm always keeping an eye out for that, by the way. Sine squared theta plus cos squared, that's 1. So that's a good sign. Yeah, good sign. Over. And then remember now this is this part here, right? I'm putting it over a common denominator. So our common denominator, we said, was sine theta times cos theta. Okay? And then that is still all over 1 over sine theta. All right. Now, like I said, sometimes it's helpful to do this, right? To keep those things separate so you can keep track of what you're doing here. But now we can start working on this, right? Because look at the top here. The top, like I said, sine squared theta plus cos squared theta. Well, that's 1. So I can call that 1 over sine theta times cos theta over 1 over sine theta. So it's like this over this, right? And then we'll do the same thing with whenever you're dividing by a fraction, is the same as multiplying by the reciprocal. So let's just write this a little different. This is 1 over sine theta times cos theta times, and then flip this guy upside down. So we've got sine theta over 1. All right, so those cancel, sine theta, sine theta. In the end here, this is the same thing as 1 over cosine theta, which is the same thing as just secant theta. Phew. Well, there you go. See, all of that mess got simplified down to just secant theta in the end there, right? This skill right here, everything we did with this one, keep this in your toolkit of tricks here, right? Of combining it under a common denominator. Because if you guys ever take calculus, this comes up a lot. We do this a ton in calculus. So yeah, this you guys will get used to doing this. I promise. Yeah. Anyway, hopefully you guys are doing okay with that. Make sure you guys do lots of practice in this unit, because a lot of it is just like I said, where you'll start doing these questions, and then like at this point right here, right? As I was doing this, I was like, oh, sine squared theta, cos squared theta. That's just from doing it so much that I'm like, that's 1, right? Like doing these lots and lots of times, you're going to come across situations where you just recognize it. And that's so much the key to this. So practice is so important in this unit, I think. So I'll leave it there.